Professor Matta got his bachelor degree in pharmaceutical sciences at the Alexandria University, Egypt, PhD at the McMaster University, Canada, and a habilitation degree at the University of Lorraine. Cherif is the head of the Department of Chemistry and Physics at Mount St. Vincent University and honorary adjunct professor at Dalhousie, Laval, and St. Mary's Universities. He's also visiting professor at the Zewail City for Science and Technology, Egypt. After completing his doctorate at the McMaster under Professor Richard Beder, Cherif was a postdoctoral researcher at the University of Toronto under the Nobel laureate Professor John Polinay, and an Isaac William Killiam postdoctoral researcher at Dalhousie University with Professor Russell Boyd. He has given more than 250 lectures in over 30 countries and has around 200 publications, including 4 books. Cherif was appointed Distinguished Visiting Professor by the Polish Ministry of Science and Higher Education in 2022-2023 and was the Atlantic Science Speaker of the Year in Chemistry in 2021-2022. He received the Mount St. Vincent University Research Excellence Award in 2017, the Lady Davis Fellowship 2016 to 2017 from the Israeli government, the NCRS AXPAS Proof by Image Jury Prize in 2016, the Molecular Graphics and Molecular Simulation Society Silver Jubilee Prize in 2009, and many others. Cherif is an elected fellow of the American Association for Advancement of Science, the African Academy of Sciences, the Royal Society of Chemistry, the Institute of Physics, the Royal Society of Biology, and the Royal Society of Arts. He was, in 2021-2022, the head of the Canada Research Chairs in Interdisciplinary Adjudication Committee of the Free Council of Canada, and is currently a director of accreditation and a member of the board of directors of the Canadian Society for Chemistry. In 2022 to 2023, he served as a member of multidisciplinary selection committee for the Tri-Council of Canada's Canada Excellent Research Chairs program. He is currently serving as second term as elected member of the Commission on Quantum Crystallography of IUCR and as a member of the Canadian National Committee on Crystallography. And today, Cherif will talk on ATP synthase more than just a biocatalyst. Cherif, the screen is yours.
Thank you so much, Paulina. Oh my God, you're making me nervous. I hope I don't disappoint you after this wonderful introduction and very generous of you. First of all, I would like to thank Professor Wozniak and Professor Dominiak for this very great opportunity to be in this forum. So the little story I'm going to tell you is recent work we have done on an enzyme, a molecular machine that is extremely interesting in my opinion, that we are perhaps proposing 2 new roles for this molecular machine in the cell. So first of all, let me, in order not to rush the acknowledge my colleagues that did the principal part of the intellectual work, which are Professor Tan Nguyen Dang at Université Laval, and Dr. Peyman Fahimi, and Dr. soon-to-be Jean-Nicolas Vigneault, who has done much of the programmer and these financial institutions. So basically what I'm going to try to convince you today is that this enzyme, as opposed to what we learn in first year, second year chemistry, that enzyme are biological catalysts, they do not interfere with the energy of the reaction, but rather they modulate the height of the energy barrier. Well, today I'm going to suggest that this enzyme has an effect, not necessarily lowering, but it could also increase the energy difference or lower the energy difference of the reaction, but also can modulate the entry of the reactant as well to the pore where it enters in the enzyme. So this is my plan. I will start by reviewing where we are, the mitochondria, which is, as you all know, the powerhouse of the cell. It is a double membrane structure. It has an outer smooth membrane and an inner corrugated membrane. This whole thing resides in the cytoplasm. Inside is where the Krebs cycle reactions occur. In the inner membrane is where you have all the electron transport chain reaction. And it is a very small organelle of the size of a bacteria. In fact, the theory says that its origin has evolved from bacteria that were incorporated in the eukaryotic cell to later become part of the eukaryotic cell. It has its own genome, etc. So the mitochondria is about, in rough numbers, 1/1,000,000th of the volume of the eukaryotic human cell, for example. So it's a very, very tiny little thing. It is the place where most, not all, but most of the energy currency of the human body is produced, or of the biological system is produced, which is adenosine triphosphate, also known as ATP. This theory that of energy transduction in biological system is credited to the late Professor Peter Mitchell, who has basically proposed it in the 60s, and after a lot of resentment from the community and fights and so on, it became now the standard accepted theory of energy transduction. Essentially, everything we eat is converted into highly reduced molecules, NADH and FADH2, that delivers hydrogen equivalent to the inner mitochondrial membrane. Then the hydrogen equivalent splits apart, where the electrons are cascaded in a series of concatenated coupled reactions that are called the electron transport chain, all exergonic, using this exergonic energy that is produced in order to push the protons against the concentration and electrical gradient into the intermembrane space here. Then the protons go through this enzyme we are about to discuss today, through a pore in the part of the enzyme that is embedded in the membrane, as you can see here. And while it goes downhill in terms of potential energy, the energy is captured in a rotatory mechanism to force the non-spontaneous reaction of inorganic phosphate incorporation in adenosine diphosphate to create ATP and water. So we are going to zoom in on this enzyme. So the enzyme is embedded, as I said, in the inner. This is a mitochondrion. You will see this is this is due to North Dakota University, this slide. So here is the inner mitochondrial membrane. We're going to zoom in. You can see the enzyme right here. These are the other complexes of the electron transport chain. So the operation of the electron transport chain is such that it creates a hydrogen ion imbalance, and then the protons enter in a pore here between this FO unit part is called the C ring part because it has a cylindrical form, and every 3 protons that enter are sufficient to drive 1 rotation. And at the end of every 3 protons that enter and go downhill, you have accumulated sufficient potential energy to create 1 ATP. In view of the time, I'm going to go quickly here. So because of the proton imbalance, you have a voltage, an electric field, and associated with a voltage across the inner membrane, with the main component of this electric field perpendicular to the membrane plane, as shown here by these arrows. To give you some number, the delta pH between the two sides of the membrane is enormous, given just 70 or 80 or 100 angstrom thickness. It's about 1 pH unit. The voltage difference is about 0.2 volts, enormous. And when you divide by the distance, you get 10 to the 7, 10 to the 8 volts per meter, so huge. Typically, in every textbook of biochemistry, you have this expression that tells you that the delta G, according to the Mitchell theory, is essentially electrical with a little bit of chemical. It could be, if I had sugar here, of course, you have an osmotic term that has nothing to do with charge. So this is just because of the imbalance in concentration, and this is due to the imbalance in charge. And given that the imbalance in concentration here or activity is that of hydrogen ion, you can convert that term into pH, taking the logarithm and so on, you can convert it into delta pH. So we have two terms, an electrical one. Psi here has nothing to do with wave function, talking about people in quantum crystallography here. So I have to be clear that psi here is the biochemist, delta psi is the biochemist designation of a potential energy, of an electrical potential difference. Delta psi is voltage difference. Faraday's constant here, and the rest is clear here. So the hypothesis behind the work, I was teaching one day biochemistry, and I realized that I was working with Professor Lou Massa on this enzyme for a completely different story. Maybe if I have time, I will explain it a little bit at the end. And I realized that the C unit here, or the FO unit, which is formed of, in humans, 8 rings, it's in fact 16, 8 and 8 outside and 8 inside rings, alpha helices. These alpha helices have a tremendous cumulative dipolar electric field due to the alignment of their hydrogen bonds and so on along the cylinder's length. So I reasoned that maybe the enzyme itself may have a component of the electric field that is parallel or anti-parallel to the electric field that is associated with the proton imbalance. Well, if such a field exists due to the charges on the surface of the protein, nothing to do with the proton imbalance, then in this case, and suppose, and this is a big suppose, we don't know, this is the hypothesis, if it is within an order of magnitude of the natural field of the proton imbalance, and it has a component, it has a projection along the z-axis here, the long axis, it may either reinforce the natural proton imbalance field, and you will have the right arrow here, or it may cancel it, and you would have a smaller arrow here, or even reverse it. I don't think it's reverse is a possibility. Otherwise, we will die. We will not create ATP. So it will weaken it. So the hypothesis is whether we can insert an extra term here just due to the delta psi of the ATP synthase itself. In fact, I am not a native English speaker, and I didn't know that word at all, what is this moonlighting means. And it turns out that moonlighting means someone that has a secondary job in the evening to increase their salary. Like suppose I'm a professor at the university in the morning and I'm working at a coffee shop in the evening, then I would be moonlighting. In fact, it's a technical term in enzyme chemistry, and it means a protein that has a secondary role, exactly. So the paper has been published a year ago in ChemCom, and it was we were fortunate to be selected on the cover, and chemistry world have found it of sufficient maybe significant to have an article about it and interview other scientists about these findings of this paper. So we were really lucky and happy with this attention. The approach we had is that my colleagues have scanned the literature and obtained the 5 best structures available in terms of resolution and cleanliness and completeness of the structure that come from a variety of different organisms. These are the technical details. I'm going quick here because I have a lot to present. You're talking about, so some of these structures come from electron microscopy, some come from X-ray diffraction, with the size of the enzyme is anywhere heavy atom-wise between 30 and 40,000 heavy atoms, something like 60 to 65,000 with the hydrogens. Number of residues is 4,000 to 5,000 residues. we have used the linearized Poisson-Boltzmann equation in order to calculate the electrostatic potential after doing some cleanup and some assumptions here. So I will show you the preliminary result of that work. So let's first agree on a coordinate system. So the z-axis here is the long axis of the molecule. The FO unit here, this is not 0, this is O for oligomycin inhibited unit. It's not 0, this is 1, but this is O. The FO unit here is embedded in the membrane. We did not take this into account. We solvated everything in water, and this is an approximation, but it's in our favor, and I can explain this in the question period. Then I would like to show you a movie. As we come down the z-axis, we were going to look downhill, like we were going to look from the top here, down the z-axis at the electrostatic potential as we go down. We slice, like salami slice this protein, chup, 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 and we look from above. So I give you the summary of the movie you're going to see. So I'm basically destroying all the suspense of the movie. At the beginning here is the intermembrane space. You would find it all red in the positive. And down there, after you leave the membrane, about 70, so anything positive, anything negative, Z minus 10, minus 5 means you are in the intermembrane space. When you reach Z is equal to 0, the proton is just entering here. And then when you reach 70-ish, 71, 75, 70, this is the coordinates where the proton just leaks out of the protein into the matrix of the mitochondrion. And you will find that that is mainly blue. So here is the movie. So this, look at this. This is minus, so you're in the gap here between the two membranes. It's still minus. It's still minus. When you reach 0, you just entered the pore, and you can see here the C ring. And this is irrelevant. This is supposed to be in the membrane, the bilipid membrane. When you reach 70, the proton has just exited. So the proton has just exited. It's all blue now. And if you keep going, you will find, for the sake of time, I will move down below. This is the end of the enzyme. You're at 200 angstrom down. So it's all blue, blue, blue. And this has nothing to do, I repeat, with the proton imbalance. This has everything to do with the way the charged residues are decorating the surface of this enzyme. So here is the summary again: red on entry, blue on exit. So how do I summarize that? So what we've done, we've taken these points with certain parameters away from the surface of the protein and up to a certain distance and so forth, and we've averaged over the entire plane. And so every plane will become a number. So I have an average potential versus a z-axis. Here it is. So this is the z-axis. So this is in the negative here. You're in the intermembrane space before the proton enters. Then 0, then 70, it just exits here. And you can see here that the average potential shoots up to the roof on entry. It creates like a barrier that regulates the entry of the protons in the FO unit, between the FO unit and the C ring, the A, it's called the A subunit. And then it fluctuates a bit. We don't really look at this very closely because that's not our interest here. But what the proton sees on exit is a big potential difference from entry to exit. So, and it does not depend on the angle. Like these are, like we've repeated this, but instead of averaging over the entire plane, we average over sectors. And you can see that the story remains more or less the same. It's the same for different organisms. So the summary of this stuff is that ATP synthase has the well-known textbook role, the putative role, that is to accelerate the phosphorylation of adenosine diphosphate into ATP to be further used in driving all the non-spontaneous biochemical reaction to completion. Second, we propose a secondary role now, and that is of modifying the delta G, not delta G double dagger, delta G of the proton translocation reaction, not of this reaction, but of an associated reaction. It's quite complicated. Like the picture I presented at the beginning is a bit misleading, but I don't know how to draw it more representative. So in terms of numbers, the numbers may be deceptively small, but remember that these delta G's are per proton. So how does this translate into biochemical energy? How does it change the way you calculate calories, for example? Well, 1 glucose is known to be approximately, because these are not stoichiometric reactions, these all depend on concentrations and so forth. So 1 glucose is roughly 30 to 35. The burning of 1 glucose unit or 1 mole of glucose creates about 30 ATPs. 1 ATP stores something like 50 kilojoules per mole under cellular conditions. In order to the synthesis of 32 ATPs, the total number of ATPs per glucose unit, that would require something like 1,600 kilojoules. This is much less than the 2,900 kilojoules that you would get from a bomb calorimeter, for example, by burning glucose. But this is the rest is of course dissipated as heat in the biochemical system. But anyway, so it's not perfectly efficient here. Of course, there is a lot of wastage. But at any rate, this is what you get per glucose in the cell roughly. Now, each ATP requires on average 3 protons to make a complete turn of the FO unit. So in other words, 1 glucose requires approximately 90 to 100 protons to be transferred per glucose unit. So that if you incorporate these numbers, these are the change in the delta G of that reaction. That is equivalent to about 5 to 30% of what is believed in, or of the textbook value. Now, of course, there is also a term at the beginning. I said it creates a potential energy barrier that could regulate the rate of proton translocation, but this is, in our opinion, much less crucial, because even though that's an exponential relation, this modulation of the energy barrier of entry of the proton, so it takes the higher end of the tail of the Boltzmann distribution, but it's very close to the thermal noise in this in this environment. So Peyman Fahimi, the person that one of the two key persons behind this work, has done some blast just out of curiosity to see how similar are these 5 structures. And here is like the lines between these are 2 sequences, primary sequences, for example, and you can see the lines indicate identity of residue, but look, the majority of the residues are very different. So in fact, this is not a symmetric matrix because the lengths are not equal of these primary sequence. So depends which one you take as a reference and you compare the other one. So, but you're talking about below 50% identity, well below 50% sometimes. And if you take similarity, of course, it's higher, because here similarity means this compares hydrophobic together, hydrophilic together, etc. So based on the type of residues, of course, it's higher than that, but still very low. But so and this is well-known phenomenon, is that like enzyme that produces the same work have very different structures. This is something that is striking, because here he is comparing the molecular electrostatic potential similarity by taking, it's a little bit like the Carbeau similarity index, if you remember from Carbeau's paper of the 80s, whereby he integrates the densities, the product of densities, and then divided by the integral of the square of the densities separately. Here, what is he doing? He's taking the trace I showed you here, this trace, and do a trace like that, for example, for each of these species, and just do the overlap of these traces. So that's how we get these numbers. And of course, there is no relation between these two, which is not surprising, but it's quite interesting as well. So one word before I leave that is ATP synthase as Maxwell demon. Completely unrelated, in 1965, there was an important paper by Johnson and Knudsen, which resolved a very long-standing paradox of the renal inefficiency of the kidney, because the kidney, if you compare the ATP used versus the osmotic work that is produced, it's dismal. It's like 0.5% efficient, while every other organ in your body is roughly 20 to 40% efficient. So why was that one so inefficient? It is argued in this Nature paper that it is because the efficiency, of course, is kind of, efficiency has an element of subjectivity because it depends what you consider as useful work. If you consider as useful work the work of sorting, in other words, of measuring bits of information there, and you factor that in, you recover the 40% just like everybody else in the body. Fantastic paper, very, very interesting paper. There was a few follow-up papers by these workers, but this is the main one. In fact, in Léon Bridouin, La science et la théorie de l'information, very famous book, translated in every language, you can't get a measurement for nothing. You can't erase this. This concept has been extended by no else than Landauer, and it's called the Landauer principle for good reason, and that every time you erase a bit of information you have to dissipate a minimum amount of entropy, and this has nothing to do with any physical arrangement. It's a necessity of nature. It's just like the Heisenberg uncertainty principle. You can't get around that. So we followed, we being Professor Lou Massa and myself, followed the steps taken by Knudsen and Johnson and applied it to the ATP synthase to discover that you need, if you take this into account, whereby you are selecting ions, protons you're authorized to enter, not protons you are inhibited to enter, prohibited to enter, and you factor that in fact, you have to add another term that is quite significant, because while it is insignificant per one operation, perhaps, but when you multiply by 100, because you need 100 protons per glucose unit, it becomes quite significant. And this dissipated heat that the mitochondrion has, that the ATP synthase has to dissipate. And no wonder, a few years ago, much later than this work with Lou Massa, came what is now known as the hot mitochondrion paradox. So people have measured the temperature of the mitochondria using fluorescence quenching at higher temperature. So they found in a very, very carefully conducted study, 17 pages, nothing but eliminating sources of error and sources of interference of the 17 pages, that there is no way around it. Mitochondria are very hot. Now that's very surprising because of the small distances. So you require, heat, you require conductivities that are extremely low, astronomically low. So what's going on here? So that created a big fuss in the literature and a huge debate between the theoreticians, and the theoreticians said the maximum you can get is 10 to the 0.0001 Kelvin. And these people are saying, no, it's 10 Kelvin. So who is right? So it's a big debate. This paper is cited perhaps 300, 400 times because of this debate. And so Mohammed Nasr, who was visiting from Zuwail City, I gave him the task of going around and looking at the literature to see if there are secondary indicators, not necessarily direct evidence, not a smoking gun, but if he can build a circumstantial case that the mitochondrion might be hotter than usual, than the other, and he did some bioinformatics work in this paper. And the main finding is that indeed, it appears that the mitochondria has an increased production of heat shock protein compared to the rest of the cell, which we presume or hypothesize that it is in order to mitigate the effect of the increased heat production in there, and it protects from the concomitant increase in reactive oxygen species production. But we didn't say by how much in this paper that I just showed you. That came up with my brilliant colleague, Dr. Peyman Fahimi, who has presented this theory, and the theory reconciles both theoreticians and experimentalists. And he went around with a very painstaking book counting of the energy produced and energy absorbed in the processes of the mitochondrion to discover the following. First of all, let's remember, a proton doesn't exist as a proton in biochemical medium. It's a hydronium ion that is hydrated. So in the intermembrane gap, it is just a hydrated hydronium ion. In order to enter the ATP synthase, previous molecular dynamic simulation studies have proven that that proton has to be enters as proton, that doesn't enter as hydronium ion. Hence, you need to desolvate, deprotonate, take the proton and enter into the FO unit of ATP synthase, and when it exits, the whole movie is reversed. These actions here need energy, and hence you have a cold spot. These actions here release energy, and hence you have a hot spot and you have a difference without violating energy conservation. So at the end of the paper, Fahimi has presented the following summary, is that you have short-lived spikes of temperature, and he calculated the temperature to be roughly of the order of magnitude that is measured by the experimentalist. And when you average this over a long time, you get exactly the magnitude that was predicted by steady state Fourier law type heat conduction physics. So there is no paradox. And most recently, and I'm almost done, the structure of the human ATP synthase have just been published in 3 months ago. So last weekend, we repeated the work on the human, and we find something a little different than what we have found before, but in the ballpark in the same direction. I apologize. I had a movie here that wasn't inserted for some reason. At any rate, in conclusion, to close my talk, the electrostatic potential difference between proton entry and exit point is within an order of magnitude of the potential difference due to the proton imbalance, and that is just due to the structure of the enzyme in itself. It's a moonlighting enzyme, as I said at the beginning. Second, it appears that there is an electrical potential barrier that regulates the rate of entry of the proton in the FO unit. Third, it seems that we need to add 2 terms in the textbook expression for the delta G of energy transduction in the mitochondrion, one related to the structure of the ATP synthase itself, the other one related to the functioning of ATP synthase as a Maxwell demon. In fact, they come with different signs. One is giving up energy, which is this term. The other one is dissipating energy. So it looks as if ATP synthase is giving with one hand to take with the other in order to keep functioning. So it has built in its own reason for existence, for longevity. And finally, the mitochondria are hot, and both theorists and experimenters are correct, but for different reasons, and maybe there is no mitochondrial paradox and no need to fight after all. Open question for future. We have to be humble here and remember to be reasoned in what we claim. We studied 5 species plus human. There are 2 million species out there, including 7,000 mammalian. So we cannot claim a general conclusion, but it's an interesting stuff at a very tiny sample of the available organism. How about Homo sapiens? It seems the preliminary result of last week that it might carry on to Homo sapiens indeed. And hence, perhaps we need to reevaluate a little bit to have a correction factor into the way we calculate caloric values of food. Third, what are is this work applicable to other things like proton uncoupler that short circuit the circuit I presented at the beginning, or in case of sodium potassium exchange pumps, for example, in nerves? Finally, decomposing the contribution of the proteins and trying to understand exactly which subunit is the most, the one that is most responsible for the observed potential difference, and whether we can use targeted mutagenesis in order to modulate this by enzyme engineering. Finally, we can redo the calculation more accurately now by placing the FO unit in the bilayer with a dielectric constant that is more akin to phospholipid bilayer instead of solvating everything in 80. That means that the result I presented you is the bottom line, is the lower end, is the lower possible end, and any results that will come here, because the lower dielectric constant of that part will be higher numbers, so the effect that I presented will be magnified for sure, but by how this awaits the results of the work that I'm doing in collaboration with Professor Anastasia Alexandrova of University of California in Los Angeles. Finally, and before I close, I make a commercial break here, since this is a quantum crystallography crowd for these two recent books. This one has been published already, Quantum Crystallography by Lulu Huang and Professor Lou Massa. And this one on electron localization, delocalization matrices, that will appear in about 3 or 4 months by Springer by Dr. Ronald Cook and Professor Paul Ayres. And at the end of this troubled time, where we suffer from all sorts of violence and turmoil in the world, I cannot think of a better thing to leave you with except the Louis Pasteur's quote here: La science n'a pas de patrie parce que le savoir est le patrimoine de l'humanité, le flambeau qui éclaire le monde. It's the science has no homeland because knowledge is the heritage of humanity, the torch that lights up the world. And John Lennon indeed imagined. Thank you very much for your attention.
Thank you very much, Cherif, for this beautiful lecture and beautiful quotation. Your lecture is now open for questions and comments.
In meantime, I have maybe a technical question. So you mentioned that in your first calculations, you embedded everything in water. Now you would like to include the contribution or the from the lipid layer. Can you also comment on or give us a bit more details how you actually computed this electrostatic potential? That was a force field approach or more sophisticated calculations?
Yeah, there are two parts of this, right? So we use the linearized Poisson-Boltzmann equation, which if you if you follow the development, there are two parts of this. There is a part that is related to the electron density of the protein, and there is a part that is related to the not the electron density, the total charge density of the protein. And there is a part that is related to the charge density of the medium, which depends on the concentration of the different ions and their interaction with the potential at that point. So it's kind of an iterative, it has to be solved iteratively. And that depends on the concentration of the ions and their charge squared. So this part, I think the question refers to that part, which is the part, how do you describe the charge density of this huge thing, 66,000 plus atoms? What we did is we have used amber charge. So I'm sorry, I'm flipping here a lot of things. Here it is. We've used amber charge. So first of all, so we put at the position of the nuclei the effective charge that comes from amber. I know it is not the best thing in the world, but what can you do with a protein that size? And then remember that the fluctuations in the biological uncertainty and fluctuation is such that an order of magnitude answer suffices. So for our purposes, it's perfectly fine. Then, of course, we had to first of all, the program that was written by Jean-Nicolas Vigneault first had to adjust this 5 structure to one common coordinate system. We've used principal component analysis in order to align them to their long axis. And then his program automatically submit these calculations after cleanup to the adaptive Poisson-Boltzmann server, APBS, which is available here for free. to calculate boxes of electrostatic potential. Then the cubes were then analyzed by his code, taking these sections, sliced perpendicularly to the z-axis. So that's the technical details here. And of course, we used monovalent, we used the concentration of the ionic strength that is known to be in the mitochondrion as described by Baker et al. In this PNAS paper here. And the interior of the protein was considered, having a dielectric constant of 6. Oh, that shouldn't have been this. Of course, I don't know why this came down. But anyway, the water was 80. The interior of the protein was a dielectric 6, dielectric constant of 6.
However, could you comment, Cherif, on such a point that some time ago, Politzer introduced many parameters which characterize electrostatic potential. I think it would be very interesting to see how these parameters change when you go through your system, whether they, at particular planes, whether they are staying at the same place, at the same location, or they move when you go deeper and deeper into the system. Have you tried to see this?
I'm not familiar. Thank you, Christoph, for your question. I'm not familiar with these parameters, but I'm open to suggestion and I'm open to collaboration. If something that really interests you and you have the time and interest to explore it together, I'm totally open. If that's something that interests you.
Thank you.
Thank you.
With proteins, you always have a question about the protonated state of each residue. Have you considered how this potential would change if you would change the protonation state of the amino acids, or how you decide?
Great question. No, we have done pH 7 for all of these calculations, but yeah, it will change. Of course, these are refinement. These are preliminary results here, but we're again. I mean, you have to probably have different protonation states at the small fragments that are outside in the intermembrane space, then the part that is embedded in the lipid bilayer, then the part that is down in the matrix of the mitochondrion. So it's really complicated problem, but it doesn't mean it cannot be done. But these are further refinement for the future. Thank you.
Your calculations have showed that there is some kind of potential barrier which has to be overcome by proton to enter the protein. What could be the function of it, or do you think it could be somehow regulated by the protein, or?
Well, first of all, we're not sure if it is, we only studied 5 structures, as I said, so it's not a general thing, but at least in these 5 structures, there is a consistent finding that you have that barrier here. Now, it seems that it allows only the highest part of the Boltzmann distribution, the protons that have the highest kinetic energy, let's say, to enter in the FO unit. Now, why is that? I have no idea. But it's an interesting observation that calls for further exploration and perhaps study.
So let us thank Cherif for this really great talk.